Okay, our next speaker is Xin Lyu, and he's going to tell us about lower bounds for differential privacy under continual observation and its implications.
Hello. Okay, so thank you for joining this talk. I will be talking about lower bounds for differential privacy under continual observation, which is a joint work with Edith, Jelani, Tamás, Uri, and a conference version with this paper appeared in Code. So let me begin with a gentle introduction. So we consider this famous model of differential privacy under continual observation pioneered by Dorknor, Pitasi, and Rothblum. Here, we want to design an algorithm A processing a sequence of online updates, and we need to report after each update certain information of interest. The privacy requirement is that the whole output vector of length t is differentially private with respect to the change of any single update, also known as the event level DP. So here we study, arguably one very basic problem. So we are interested in monitoring a dynamic environment and react quickly when certain events of interest show up. For example, this can happen. Maybe you want to keep up on trends in Twitter or Google search. For example, if everyone starts Googling WWDC, you know something interesting is going to happen. Then there are a couple of other examples. And here, the question we are interested in is how many events must show up before the best private algorithm can make a reaction? So just as a warm-up, if you react as soon as one event is detected, that's a clear violation of privacy. And so let me formalize this problem with a math language. So we have a sequence of online updates, U1 through UT, where each UI denotes where there is an event at time step Ti. And the algorithm needs to report pass or halt after each update. To be considered correct, we cannot have false positives, meaning that if the algorithm halts at time I, there has to be at least one among U1 through UI. And in terms of privacy, standard epsilon delta DP with respect to any single update being 0 or 1. And to mirror your utility, let's say your algorithm halts at around I, which is itself a random variable, to minimize the number of ones you have seen so far. So clearly, smaller is better. And the question is, fixing these relevant parameters of interest, what is the optimal utility? So just a quick summary. We want to monitor a sequence of 0 and 1s and halt after seeing at least 1, and minimize the number of 1s before halting and be differentially private. There is this famous sparse vector technique, also known as above threshold, which solves exactly this problem with epsilon 0 DP guarantee. And it is in expectation and with high probability of halt after seeing roughly log t many ones. And there is you can also prove an easy packing lower bound, saying that any pure DP algorithm cannot have utility below this threshold. So cool. So for a reasonable summary for prior results is that if you only consider pure DP algorithms, log t is just the correct answer. So we are interested in studying whether there could be an improvement with approximate differential privacy with a somewhat large delta. So say delta is 1 over log t. So the standard practice of DP usually sets delta to be inverse polynomial in the size of our data set. However, we argue that the case of sparse string, meaning that the number of events is far less than t, is a well-motivated setting. And in that case, we set in delta to be inverse polynomial in the number of events is a standard practice. Right, but unfortunately, we show the answer is negative. So we say that for any delta that is less than 1 over log t, there is no epsilon comma delta DP algorithm that can give you a little o of log t utility. So this is saying you cannot really hope for an improvement over about threshold, even in the large delta regime. So before going to the proof, I want to quickly mention that this is in some sense a truly online lower bound, because the packing lower bound is also holds for the offline version of the problem. So the sigma log t hardness remains, even the algorithm is giving U1 through UT in a single batch. And our lower bounds, in contrast, is a kind of inherently online one, because if you are given all these updates in a single batch, you can identify index to a time step to halt with this private median algorithm, and it can offer you a utility of roughly log star t times log over delta. Here, log star denotes the iterated logarithm, the number of logs you need to take before making your quantity less than 1. Okay, cool. So let me go to the a quick proof overview. So just to recap the problem, you want to monitor the sequence of 0 and 1s, and you want to halt after seeing at least 1. You want to minimize the number of 1s before halting, which we refer to as utility. And you want to be differentially private. So here we do a proof by contradiction. Suppose you have such an algorithm with utility little log t, and we derive a contradiction. So for technical convenience, we suppose e to the epsilon is less than 1.5. So here, this is really saying we are focusing on a small epsilon regime. So you can easily turn this lower bounds into to work for all range of epsilon by paying a price of roughly 1 over epsilon, but that's, I guess, standard. Okay, so to set up the proof, let A to be an algorithm that we are going to analyze. So if you assume A is a correct algorithm, that means if I feed you the input of all 0 sequences, you are not supposed to halt. So let's say A halts with probability less than 1%. And then our proof, we are trying to find an input with at least log t ones, but A halts on this input with probability at most 1/2. So that's clearly saying the algorithm is not correct on this new input. So one motivating attempt is, let's say, how about I just append log t updates at the very beginning of my stream? Then you have this standard group privacy bound, which tells you that the algorithm halts with probability at most 0.01 times e to the k epsilon. And this is a vacuous bound as soon as k gets to as large as 1 over epsilon. So you can say this multiplicative factor e to the epsilon is quite expensive here. And so you want to devise one method to really reduce this blow up. And here we, to do that, we explore both the long stream of the interaction and also the onliness of the algorithm. Here's how we do it. So let's say we just append a single update at the beginning of the stream and see what happens. So we do so first of all, the probability of halting can bump up to 0.01 times e to epsilon plus delta across the whole stream, because you need the whole output vector to be differentially private. And then we ask ourselves, is the algorithm more likely to halt on the first or the second half of the stream? So if the algorithm is more likely to halt on the first half, it implies conditionally not halting on the first half. The probability of halting on the second half of the stream is actually small. So specifically, it's less than the original quantity divided by 2. And in that case, what we do is we are trying to insert more updates into the second half of the stream. And by doing that, since we are analyzing an online algorithm, this have no impact on the first half of the stream. So in only half of this probability mass, we will suffer from the e to epsilon blow up from now on. And the second case is actually, what if your algorithm more likely to halt on the first half of the stream? In that case, we simply ignore the second half of your stream, and we try to recursively insert more updates into the first half of your stream. And so our construction will guarantee eventually we'll insert at least log t once before time step t over 2. So eventually the stream from t over 2 over t to t is no longer relevant, because if your algorithm didn't halt up to time t over 2, that's already considered a utility failure. And overall, by doing this manipulation, we can reduce the e to epsilon blow up to a half times e to epsilon shrinkage. And finally, you can use a geometric series to bound the overall halting probability. So if you are a math genius, you can imagine the whole detail right now. I mean, if not, don't worry, the proof is only 1 page. All right, let me mention all the applications we have. So we have applications on online counting, learning, and query releasing. So I mean, a direct implication of our result is saying online counter has error omega log t even for smart streams, because I mean, detecting events is clearly easier than counting events. And we are saying even for detecting events, you need to see at least log t events to make it noticeable reactions. And to compare previously, we have omega log number of events lower bound known by Hesinger, Upadi, and Upadi. But they also have a stronger lower bound in terms of L2 error metric. And for L infinity metric, I think there is still open problem to close the gap between log t and log t to 1.5. if we consider the case of downstream. Anyway, I also want to highlight that if you consider offline algorithm, so namely you are given an array of 0 and 1s and you want to release all the prefix sums, then you can actually design algorithm by doing, divide and conquer binary divide and conquer stuff to solve the problem with error log star t times polylog number of events. So that means our result separates the online and offline versions of the counting or releasing prefix sum problem. And the second application is about online learners. So we can prove that online learner makes log t mistakes to learn simple classes, even as simple as point classes with t points. And this is a hypothesis class with little stone dimension 1. So non-privately, after making at most one mistake, you can identify the correct hypothesis and make no mistake from now on. And what we say is, so imagine you have a sequence of queries, which are all kind of trivial queries. Then your algorithm has no clue what the true hypothesis is. And our lower bound then says, look, you can modify your query stream and insert log t interesting queries into the stream such that your algorithm reacts slowly to these surprises. So the algorithm will keep making mistakes on those, surprise queries. That's how we get these log t mistakes, kind of intuitive. And I also want to highlight a concurrent work by Dmitry, Szabo, and Sanyo, which shows a stronger lower bound on the assumption on the algorithms. So there are still a slight technical gap between what we conjecture to be true and what we can prove. So, if you are interested, I'm happy to talk offline. The last application we have is about lower bounds for answering online threshold queries. So here the setting is you are given n real numbers from 0 to 1, and you want to answer t threshold queries. Each query is specified a parameter q sub I, and you want to answer how many data points in your data are below this threshold. And we say, if you want to answer t such queries, you must pay an additive error of log t, separating itself from the non-offline bound of log star t. So not like these first two applications, the last one, to use our technique to prove low bound for the last application, it requires a little bit more creativity and a certain application of Ramsey theory. But I'm happy to talk offline for the details if you are interested. So with that in mind, let me wrap up. So in this work, we prove a first set of online lower bounds against natural DP tasks. And what we say is in an online DP setting, the algorithm usually needs to see log t interesting events to show up before making any noticeable reaction. And this happens as soon as your delta is, mildly small. And we derive several consequences for online private algorithm design, including counting learning and query releasing. And I think that's it. I'm happy to take questions. Thank you for your attention.
Probably have time for one quick question. Questions.
Jens, so you emphasize this large delta, I guess in part to get the separations between online and offline setting.
Yeah.
But for the small, clearly the lower bounds also apply in the small delta regime. Were the results already known in the small delta regime, or are they also new when delta is, say, polynomially small in T?
I think if delta is polynomially small in T, packing already gives you a log 1 or delta lower bounds, which is log T.
I see.
So.
And that's true for all the applications that you were talking about as well, I guess, probably.
I think so. Yeah.
Thanks.
All right, let's thank the speaker again.